Welcome to The Debate. Imagine, just for a second, that you are strapped into this supposedly revolutionary new spacecraft. The engines are roaring and the entire cabin is vibrating with, millions of pounds of thrust.
Right, the noise is absolutely deafening. The control panels are glowing and you can practically feel the structural limits of the machine just being pushed to the absolute breaking point.
Exactly. You feel all of that immense power, but then you look down at the instrument panel and the speedometer says you are barely crawling along at like 10 miles an hour.
Yeah, it's a total disconnect.
It really is. That jarring disconnect between the sheer technological thrust you are feeling and the sluggish progress you're actually measuring, well, that is the exact state of the global economy right now. I mean, we have the roaring engine of artificial intelligence, a technology that is clearly achieving these astonishing cognitive milestones.
Yet, if you look at the actual macroeconomic data, the actual numbers on how much a single human worker gets done in an hour, our measured aggregate labor productivity growth has literally been cut in half over the past decade. We dropped from a robust 2.8% annual growth rate down to an agonizingly slow 1.3%. The economic speedometer it isn't moving.
Which brings us to the central tension we are exploring today, the modern productivity paradox. We're looking at exactly why these numbers don't match up. And to be clear on where I stand, I represent the view that AI is a general-purpose technology experiencing a completely natural implementation lag, and that scaling computation is inevitably going to overcome these deployment hurdles to drive massive productivity gains.
Right. And I represent the opposing perspective, which is that the staggering physical energy requirements, the hardware limits, and the incredibly brittle nature of real-world deployment will permanently constrain AI's actual economic impact.
So, to understand why I am so confident that the speedometer is about to catch up with the engine, we really have to look at a historical principle known as Rich Sutton's bitter lesson. For, 70 years now, AI research has taught us one consistently bitter pill to swallow, which is that clever human engineering always eventually loses to raw computation.
Meaning researchers trying to perfectly design the system themselves?
Right, exactly. Researchers used to spend decades trying to manually code human knowledge into systems. They would try to teach a chess program how to think about chess, or manually program edge detection rules into computer vision algorithms.
Handcrafting the intelligence, essentially.
Yeah, exactly. But every single time, as Moore's law made massive computation available, simple neural networks processing vast amounts of raw data completely obliterated the performance of those handcrafted models. The ultimate driver of progress isn't human design at all. It is raw compute.
Okay, but how does that connect to the missing productivity today?
Well, if you're looking at the stock market right now, you might be thinking, how can AI be struggling to boost productivity? The numbers are huge. But you have to separate stock valuation from measurable human labor productivity. The reason we don't see this compute translating into the economic statistics yet is basically an illusion caused by mismeasurement.
You're talking about intangible capital.
Precisely. Firms are pouring billions of dollars into intangible capital. We're talking new software infrastructure, entirely new data pipelines, massive retraining programs, and just, fundamental organizational restructuring.
Right, because you don't just plug an LLM into a Fortune 500 company and instantly double your output.
Exactly. You practically have to rebuild the company from the ground up. And this massive spend suppresses our measured productivity in the short term. I mean, isn't our current panic over low productivity remarkably similar to looking at the 1910s when factories were first being electrified?
The dynamo paradox.
Right. The electrical power was physically there, but the massive productivity gains simply didn't appear in the data until the 1920s, well after the physical layout of the factory floor was completely reinvented to actually utilize small electric motors.
Okay, I hear that. But the problem with relying on the bitter lesson as some sort of guarantee of future economic dominance is that it treats computation as an infinite, entirely frictionless resource.
Which it practically has been for software.
For software, sure. But it operates in this theoretical vacuum, completely ignoring the staggering physical footprint required to scale these systems in reality. We are running headfirst into a hard energy wall. We literally don't have the power grid to support what you're imagining.
Wait, you think the energy limits are a hard stop? Like permanent?
I absolutely do. Look at generative AI inference. And just to clarify, that's the phase where the model actually generates responses for users in real time, not the initial training phase. Inference is incredibly power-hungry. If a standard search engine company were to integrate a large language model into every single search query, the physical hardware required would consume up to 29.2 terawatt-hours of electricity annually.
Wow.
Yeah. Just to put that in perspective, that is equivalent to the total energy consumption of the entire country of Ireland.
That's a big number.
It's massive. And beyond the energy footprint, we have to look at how these systems behave in the physical world. Deployment is bottlenecked by the inherently unpredictable, messy nature of reality, which requires constant human intervention. The moment you have to persistently keep a human in the loop to supervise an AI, you destroy the very labor efficiency that the technology was supposed to provide in the first place.
Okay, let's unpack that, starting with the physical energy wall. Because I think the narrative around energy consumption deeply underestimates the historical trajectory of hardware innovation.
I'm listening.
The theoretical power of computation always encounters physical bottlenecks, right? And the engineering community consistently innovates around them. Hardware efficiency is improving at a rate that will absolutely neutralize this island-sized energy problem.
Neutralize it entirely? I mean, that's quite a claim.
It is, but look at the mechanism of how we build these models now. Take Google's Generalist Language Model, or GLAM. By utilizing more efficient architectural designs, specifically something called sparse activation, they drastically cut power use.
Right, the routing mechanisms.
Exactly. And if you aren't familiar with sparse activation, think of it like lighting a house. Instead of turning on the lights in every single room just to walk to the kitchen, sparse activation only triggers the specific neural pathways needed for a specific task. Because of this, GLAM actually used 2.8 times less energy during training than earlier models like GPT-3, despite having 7 times more parameters.
Okay, yes, the per-query efficiency goes up.
Right. And as this compute becomes exponentially more efficient, the economic incentives will drive widespread, sustainable deployment. We don't just scale brute force anymore, we scale architectural intelligence.
I come at it from a different way. That efficiency argument is fascinating on a technical level, but it completely ignores a fundamental economic concept known as Jevons paradox.
Ah, yes, the coal paradox.
Exactly. Back in 1865, William Stanley Jevons looked at these newly invented, highly efficient steam engines. Everyone thought, great, the engines use less coal, so we will obviously save our national coal reserves. But Jevons noticed the exact opposite happened.
Because they got cheaper to run.
Right. Because the engines were more efficient, coal power became incredibly cheap and universally useful. So instead of saving coal, total consumption skyrocketed. We ended up burning magnitudes more of it, and we are doing the exact same thing with AI today.
Because, again, the efficiency drives down the cost of using the AI.
Yes. As these models become more efficient to run with things like sparse activation, the demand for them just explodes. We integrate them into everything: phones, cars, refrigerators, customer service bots. This vastly expands the overall energy footprint rather than shrinking it. I mean, we are already seeing a trend called Mining 2.0, where obsolete, highly energy-inefficient crypto mining GPUs are being rapidly repurposed to run AI tasks.
Which is a clever use of old hardware, to be fair.
But that shift alone threatens to consume an additional 16.1 terawatt-hours of power. And even if we could miraculously find the energy on the grid, we simply do not have the hardware supply chain.
You mean the chip fabrication?
It's more than just printing the silicon chips. These systems rely on incredibly complex physical packaging, like TSMC's CoWoS, that's chip on wafer on substrate.
Right, the actual assembly of the units.
Exactly. It's not enough to just make a fast chip. You have to physically stack them and wire them together so they can communicate at light speed without melting each other. It is a massive material science problem. TSMC is facing years-long delays just to build the physical factories required to reach the volume production that AI companies are demanding today. You can't just wish these physical supply chains into existence with a quick software update.
Okay, I see what you think that, but let me give you a different perspective here. Isn't citing current TSMC packaging bottlenecks exactly like arguing in the 1990s that the internet would inherently fail because we didn't have enough fiber optic cables laid in the ground yet?
Well, no, because the physical constraints of laying cable were real, and it took a decade to solve.
Yes, but it was solved. That's my point. Physical bottlenecks are always the loudest constraint right before they are systematically dismantled by capital investment. Market forces always expand physical infrastructure to capture massive economic value.
Assuming the physics allows for it.
Sure. And yes, TSMC volume production for new CoWoS packaging plants might be delayed to 2027, but the billions in capital are already flowing. The factories will be built, the microplumbing will be solved. And this brings us right back to the J-curve of mismeasurement I mentioned earlier.
The idea that things look economically bad before they look historically great.
Right, exactly. We are currently in the deep trough of the J-curve, where massive amounts of money are being spent creating unmeasured capital. Take autonomous vehicles as an example. Between 2014 and 2017 alone, an estimated $80 billion was poured into AV development.
Which is a staggering amount of money.
It is, and right now, on a macroeconomic spreadsheet, that looks like a massive drag on productivity because it is a mountain of labor and capital input without a corresponding final consumer output. The speedometer reads 0, but once the technology matures and that implementation lag is resolved, the math flips violently.
How so?
If autonomous vehicles eventually replace just a fraction of motor vehicle operators, say, reducing 3.5 million drivers down to 1.5 million, that single shift yields a direct 1.7% boost to aggregate labor productivity. The investment pays off eventually.
Look, I'm sorry, but I just don't buy that. Let me tell you why.
Go for it.
The entire premise of the J-curve assumes a smooth, inevitable transition from the messy investment phase to a flawless execution phase. But real-world deployment is incredibly brittle, and it does not scale the way digital software does. You brought up autonomous vehicles. Let's look at exactly what happened with AVs in San Francisco in December 2025.
Oh.
The massive power outage.
Yes, a citywide blackout.
The traffic lights went completely dark across the city. Now, the AI driving the Waymo vehicles theoretically worked according to its programming, right? It correctly identified the dark signals and treated them as four-way stops. But it completely lacked human common sense.
Well, it lacked social intuition.
Exactly. Think about how human beings actually cross a dead intersection. You inch forward, you make eye contact with the other drivers, a pedestrian waves you on with a micro-expression. It is a highly complex, unwritten social negotiation.
And the AI couldn't parse that social contract.
It literally lacks the sensory apparatus and the training to read a pedestrian's body language in the dark. So what happened? The cars froze. They constantly required remote human confirmation from a call center before proceeding.
Right, the fail-safe mechanism triggered.
But because there were 7,000 dark signals across the city, this created a massive backlog of requests, effectively paralyzing the intersections with stalled vehicles. This is the reality of physical deployment. The persistent need for a human in the loop to handle these edge cases completely ruins the profitability and the pristine productivity metrics that your theoretical J-curve predicts.
That's an interesting point, though I would frame it differently. I completely concede that the San Francisco blackout was a mess, and the social negotiation of driving is deeply complex.
It's chaotic.
It is. But even if a system requires human oversight during extreme edge cases like a massive catastrophic citywide blackout, replacing the routine driving tasks 99% of the time still fundamentally alters the labor equation. You don't need flawless autonomy to get historic productivity.
But if you still have to pay humans to sit in a control room staring at screens, where is the labor savings?
We have historical precedent for this in other sectors. Look at call centers. There are, over 2 million people working in call centers in the U.S.?
Something like that, yeah.
AI doesn't need to replace 100% of human agents to be economically transformative. By handling 60 to 70% of the basic, repetitive queries, algorithmically checking balances, resetting passwords, using intelligent voice tools, we still free up massive amounts of human capital. It still boosts aggregate labor productivity significantly.
But driving isn't resetting a password.
The transition doesn't have to be perfect to be profoundly impactful, is my point.
The bitter lesson tells us that the edge cases you're talking about, the chaotic social negotiations at a four-way stop, are ultimately just data problems. They are complexities that we currently think require innate human intuition, but they will inevitably be solved by scaling computation and exposing the models to more reinforcement learning.
But you are casually equating digital information processing, like parsing a password reset in a call center, with maneuvering a 2-ton physical object in a dynamic environment.
There is a massive chasm between general digital methods and physical embodiment.
I think they're on the same spectrum.
I disagree. Let's contrast two areas of aerospace and robotics to illustrate this mechanism. SpaceX achieved a staggering 38% year-over-year launch growth with the Falcon 9 over an 8-year period. Why? Because while rocket science is incredibly difficult, orbital mechanics operate in a predictable, largely empty physical vacuum. You can model it perfectly. There is practically no friction in space.
Okay, and terrestrial robotics?
Right. Now contrast SpaceX with terrestrial robotics. Rodney Brooks, who is one of the pioneers of robotics, highlighted in his 2026 predictions that deployable dexterity in humanoid robots remains absolutely pathetic compared to human hands.
Pathetic is a strong word.
His word, not mine, and he argues it will remain pathetic far beyond 2036. The physical world is messy, chaotic, and governed by friction. A robotic hand trying to fold a laundry shirt has to deal with the infinite topological variations of cotton. The mechanical systems, the actual physical actuators, and the complex safeguards needed to keep an AI safely boxed in during real-world physical interactions simply haven't been invented yet. You cannot solve physical dexterity and safety just by throwing more cloud compute at a server farm.
See, I'm not convinced by that line of reasoning because you're treating the physical world as permanently immune to computation, which is exactly the trap the bitter lesson warns us against.
How so? The laws of physics aren't just lines of code?
No, but the way we master them is, think about computer vision. I mentioned it earlier. Early researchers tried to manually program rules to help machines see objects. They literally coded edge detection parameters. It failed completely.
Right.
But when deep neural networks were allowed to just ingest millions of raw images and figure out, say, catness on their own, error rates on the ImageNet database dropped from 30% to under 5%. That surpassed human benchmarks. And that exact same trajectory is happening right now in physical automation through simulated learning and cloud robotics.
You're talking about training robots in virtual environments.
Exactly. If a robot in a lab learns to unscrew a bottle cap or sweep a floor, that skill doesn't remain isolated in that one machine. It is instantly shared across a global network of robots. Waymo's autonomous vehicles drive 25,000 real miles a week on physical roads, sure, but they drive 19 million simulated miles a week in the cloud.
But a simulation is just a simulation.
They are mastering chaotic superhuman performance in highly complex simulated environments and then transferring those weights directly to the physical hardware. It is only a matter of scale and time before physical dexterity is solved by the exact same mechanism that solved computer vision.
That's a compelling argument, but have you considered that transferring simulated skills into a physical robot doesn't bypass the laws of thermodynamics or the limits of material science?
I mean, no, but
A neural network might learn the perfect path to unscrew a bottle cap in a perfect digital simulation. But the physical actuators in a humanoid robot still have to execute that movement in the real world without stripping the gears, overheating the battery, or crushing the glass object.
the hardware will catch up to the software. It always does.
The bitter lesson works wonderfully in the purely digital realm of Go or chess, where the rules are mathematically fixed and the board is perfectly observable. But when you move into physical embodiment, the hardware itself becomes the limiting factor, and we come right back to the energy and the infrastructure grid.
Right, the 29.2 terawatt hours.
Exactly. Even if we do figure out the actuators to gently unscrew that bottle cap, the sheer volume of computing power required to process that real-time sensory motor control at a global scale brings us crashing back into Jevons paradox. The physical world doesn't just resist computation, it taxes it heavily.
Look, I think we've mapped the boundaries of this perfectly. To sort of summarize my position here, we have to look past the immediate localized friction, the dark intersections, the current TSMC packaging bottlenecks, and recognize the broader macroeconomic cycle at play. The current productivity paradox is exactly that, a temporary paradox.
A waiting game.
Yes. It is an illusion hiding the massive, unprecedented accumulation of intangible capital beneath the surface. Companies are fundamentally rebuilding their factory floors, their software, and their organizational structures, which suppresses measured output today but sets the stage for exponential growth tomorrow. The bitter lesson of the last 70 years dictates that compute-driven general models will inevitably overcome our current deployment hurdles. Just as the electrification of factories in the 1920s required massive physical restructuring before the productivity exploded, our current investments in hardware, simulation, and scaling will inevitably unlock the full economic potential of AI.
And to summarize my perspective, acknowledging the hard limits of physical reality is not pessimism, it is necessary realism. We cannot casually extrapolate the smooth success of digital software into the physical world while completely ignoring the toll it takes. The staggering energy requirements of the inference phase, the compounding reality of Jevons paradox pushing our grids to the limit, the strict supply ceilings on physical hardware packaging, and the persistent need for human intuition in unpredictable real-world environments, those represent hard physical limits. Raw computation is incredibly powerful, yes, but it cannot magically bypass the constraints of the physical grid and the chaotic unpredictability of the human environment.
Yet I think where we absolutely converge today is on the profound capability of the technology itself. Despite the friction of deployment we've talked about, we both agree that these foundational models are achieving astonishing cognitive milestones, whether that's in processing natural language, recognizing images, or simulating complex environments.
Well, we absolutely agree on that. And we also agreed that our current backward-looking economic statistics, the speedometer we are all staring at, fundamentally fail to capture the true complexity of the transition we are living through right now. The measurements are lagging way behind the reality on the ground.
Which really underscores the incredible value of exactly this kind of rigorous exchange. Understanding both the incredible theoretical power of scaling computation and the hard, unyielding physical realities of deployment is absolutely crucial if we want to fully grasp the timeline of this technological transformation. So we encourage all of our listeners to dive into the historical productivity data themselves. Look at the electrification of the 1920s, examine the energy footprints of these massive models, and form your own conclusions.
There is certainly a lot more to explore in the source material, from the fascinating specifics of how we actually calculate total factor productivity to the brutal engineering challenges of robotic dexterity.
So keep your eyes on the data. You might feel the engines roaring beneath you, but it's up to us to figure out why the speedometer hasn't moved yet and whether it ever will.